Hello, I hope you can see me. I'm recording from my mom's house. The lighting here is good. The microphone is good. So today we're going to talk about this basics of bonding. So we discussed about ionic and covalent bond in terms of what happens inside the molecule. So those are called intramolecular bonds. So the bonds inside the molecules. Now we're going to discuss intermolecular bonds, what happens outside of the molecule. Uh, Again, it's very good if you can just read this part here because this will tell you all the basics that you need to know. I will, however, review it right now, and then I will give you in the next few videos about advanced knowledge that you actually need for AP. So first of all, I made this for you guys. So metallic bond is something that is explained in that little book, but just for now, look at this. So metallic bonds are characteristic of transition metals. Why? Transition metals have a d orbital in the last energy level. That's actually why we don't study them, because that is a very funky thing. Sometimes they have it, sometimes they don't. But one thing that is very special about all of these transition metals is that the d orbitals that they have is very large. So these orbitals are much bigger than normal S&P orbitals. So what happens in d elements is this. See, this is iron, and iron usually forms an ion of Fe2+. So what happens now is each of these irons right here has huge d orbitals around it. And these d orbitals from each of these elements, they all overlap. Remember what we said. In covalent bond, you have only two atoms, neighboring atoms, overlapping s or p orbitals. Well, you can see here that actually all of the atoms of the transition metals overlap d orbitals. So it's basically a bond between all of them together. That's the reason why metals are so strong. What they can't melt, they're very easy to they're impossible to vaporize, but they're difficult even to melt. And that's also why they conduct electricity. We'll talk about that later. For now, what I want you to remember is that this bond is extremely strong because there is an overlap of d orbitals. Remember these words that I put here because they are something that is very important for AP and also for competition. So in metals, in transition metals, there are overlapping d orbitals and delocalized electrons. What does this mean? See, each of these electrons present here is shared between all of them. You can see why this is so much stronger than covalent bond when you have sharing of electrons in the bond between two atoms. Well, here, all of the atoms share all of the electrons. So technically speaking, each iron atom is bonded with all the other iron atoms with thousands and billions and trillions around it. That's why that bond is so strong. This bond is also similar to ionic because you can't really tell where one atom or one molecule ends. So this is at the same time intermolecular bond and intramolecular bond. So it's at the same time inside and outside because you can't tell what's inside, what's outside. Then we've got ionic bond. There's nothing much here to add. So let's say this is, for example, NaCl, and Na is plus, right? And Cl is minus. So they form this type of lattice. You've seen this picture before. So each minus is bonded with 6 pluses, and each plus is bonded with 6 minuses, and they form this giant molecular structure called a lattice. And again, this is much stronger than covalent bonds because you don't have bonding between two atoms. You have bonding between all of them, basically, in this huge cage-like structure called a lattice. Remember, these are the key words for ionic bonds. So electrons are transferred from sodium to chlorine, or from a less electronegative atom to a more electronegative atom. Then ions are formed, and then the bond between these two ions, these pluses and minuses, is basically electrostatic in nature. You will see sometimes in these questions the term Coulomb forces. There's one formula connected with that. I will show you that later, not very important, especially because Coulomb forces are, you should think about them just as a simple attraction between plus and minus. So this connection is basically, this bond, the ionic bond, is basically just a connection between plus and minus. But again, it's really strong just because of the lattice structure. However, if I remove this and I talk about this, let's talk about covalent bonds. So in a covalent bond, you have a distinction between what is inside the molecule and what is outside. See, this is one molecule, for example, of HF. This is an example for covalent polar bond. Remember what we said. If the difference between these two atoms, the difference in electronegativity is bigger than 0.5, that's covalent polar. So what happens here? Hydrogen has electronegativity of 2.2, fluorine 3.98. So this side of the molecule becomes positive. This side of the molecule becomes negative, and you have this structure called the dipole formed. What is a dipole? A dipole just means that one side of that molecule, the side which has a less electronegative atom, is partially positive, and the other side is partially negative. And this kind of structure is called a dipole. So this is what happens inside of the molecule. However, how about outside? So you have here a list of things. So intermolecular bonds, for anything that is covalent, especially what is covalent polar, you have these three types of bonds. Number one, hydrogen bond is the strongest. It's weaker than metallic and ionic, but it's the stronger than dipole in London. So you have number one, hydrogen bond. Number two, dipole. I know, stupid name. And number three, London or van der Waals attractions or van der Waals forces. Has the same meaning. You will see both of these terms in different books. And again, remember that covalent bonds are electron sharing. So this bond here is formed by hydrogen and fluorine sharing electrons by overlapping orbitals, but overlapping s and p orbitals, while metallic is d orbitals. It's completely different. Now take a look at this hydrogen bond. So what is a hydrogen bond? The real answer is nobody knows. So the scientists still have not determined what is a hydrogen bond, what its nature is. However, we do know that hydrogen bond is formed if there is a hydrogen in the atom which is bonded with oxygen, nitrogen, fluorine, or chlorine. There is a star and asterisk here. Why? Because in some books they don't count fluorine to form a hydrogen bond. Here we will count it. So again, if you have hydrogen bonded with fluorine, this is one molecule, right? And this is another molecule. However, between them, there is a hydrogen bond. This is an international symbol. You should remember this. So the hydrogen bond is marked by a broken line. But the next atom here, you got, again, hydrogen bond between H and then F. And then you've got, I mean, even here you have another atom probably, right? Because there's billions of them. Like this, and you got another one here, and here you have a hydrogen bond, and so on. I will tell you about hydrogen bond more later when we compare different ability of different molecules to form hydrogen bonds. Now the next bond is dipole, and this is a dipole bond. So we're taking an example of HF. Why again HF? Because you see here that actually HF can form all three types of bonds. HF can form a hydrogen bond, can form a dipole bond, and can even form London dispersion, actually van der Waals' attraction bond. So H and F are bonded with a covalent bond. This side is positive, this side is negative. This is a dipole. But next door, you have another HF. So now this HF will turn, this dipole will turn in such a way that this plus is close to this minus simply because, again, plus and minus attract. And then you have this molecule where the plus will be close to this minus for the same reason. This minus here, you will have that happen everywhere. So this minus will go here. Another one will come here with the plus. So they will kind of get connected intermolecularly. So the molecules will be connected with this dipole attraction. So it's a simple attraction between plus and minus. This is weaker than a hydrogen bond, but it's stronger than the next one. And the next one is, of course, London dispersion forces, or van der Waals attractions. So every molecule, every covalent molecule has this. So whenever they ask you, they give you a molecule, I don't know, CH4, it has London dispersion. H2 has London dispersion. Everyone has London dispersion. Even ionic and metallic molecules have these. But the thing is, London dispersion forces are so weak. They're the weakest type of bonding of any type. So when we talk about metallic and ionic bonds, we usually don't talk about them because they're much weaker than anything else. So what happens is, well, see, London dispersion forces are basically about probability. Let's say I have one molecule, doesn't matter which one. And inside we have some electrons, you have protons, neutrons, and electrons, but the electrons move. At one moment in time, this thing will happen, this thing here. So on one side of the molecule, the electrons at one moment will be bunched up on this right side, and then the protons will be bunched up on this side. What will happen then? The next molecule, the neighboring molecule, because there are minuses here, the minuses of this molecule will escape. Will escape to this side. What am I doing? Sorry, guys. Should work now. So there'll be minuses here because these minuses will go away from this minus and the pluses will bunch up here. And then you see this looks similar to a dipole, but this dipole is called an induced dipole. It is temporary. It's just there for 1 second and then disappears the next second, which makes it very weak. And you will see that all nonpolar covalent molecules have only London dispersion because there is no dipole, there is no hydrogen bond, they only have London dispersion. So remember that if you have something like this, something simple like HH, how is this connected with another HH? Let's say there's another HH here. There is no hydrogen bond, there is no possibility of dipole, but there is always London. So when they give you a non-polar covalent bond, remember just to say London. Okay, this is fast. Let's talk about the next one. If I can stop this, that is. Okay.